welcome. Today we're pulling back the curtain on machine learning and its incredible power to predict the future. From your email inbox to the engines on an airplane, computers are making these predictions all the time. But how? How do they actually do it? Well, let's dive in and find out. It really all starts with a question you probably see a dozen times a day. An email lands in your inbox. How does the computer decide if it's junk or if it's something you actually need to see? Now, this isn't just a random guess. There's a very calculated decision happening behind the scenes. And if you can understand that one decision, you're on your way to understanding the whole world of machine learning prediction. So here's the big secret. Almost every single prediction problem in machine learning boils down to one of two things. On one hand, you have classification. That's all about predicting a category, like spam or not spam. On the other hand, you have regression, which is all about predicting a specific number, like what's the temperature going to be tomorrow? That's it. Is it a category or is it a number? Let's look at the tools for each. All right, first up, let's crack open the classification toolkit. These are the algorithms that answer that big question. Which group does this thing belong to? We're going to break down some of the most popular methods, and you'll see they're actually way more intuitive than their fancy names sound. Okay, imagine you're just trying to make a decision by following a flowchart. We've all done it, right? You ask a simple yes or no question, and your answer sends you down one path or another, until bam, you hit a final conclusion. Well, that exact same logic powers our very first algorithm. And that, right there, is a decision tree. It's beautiful in its simplicity. So in this example from engineering, the model looks at a vibration signal from a machine, and it asks a simple question. Is the total energy of the signal, what engineers call its RMS value, is it above a certain level? If the answer is yes, it predicts, uh-oh, this part is faulty. If no, it predicts, everything's healthy. It's a super simple, really visual, and surprisingly effective way to classify stuff. But, what happens when just following one set of rules isn't quite good enough? A single decision tree is kind of like asking just one expert for their opinion. They might be brilliant, but they could have a blind spot. They could be just a little bit off. So how do we get an answer that's more reliable? Yeah, relying on just one of these trees can be pretty risky. Small changes in the data you train it on can lead to a completely different set of rules, which makes it kind of unstable. It can also get a little too good at memorizing the training data. We call that overfitting, and that means it really struggles when it sees brand new data out in the real world. So what's the solution? You build a random forest. Instead of just one expert, you bring in a whole panel, hundreds of different decision trees. Each tree gets to cast its own vote, and the final prediction is simply whatever the majority decides. This wisdom of the crowd approach is incredibly powerful and makes the final answer way more stable and way more accurate. Okay, our next tool in the kit is the support vector machine, or just SVM. So picture this. You've got two different groups of dots on a chart. You could draw a bunch of different lines to separate them, right? Well, the SVM is specifically designed to find the one single best line, the one that creates the widest possible street or margin between those two groups. It's all about finding the clearest possible boundary. And that's the whole point, to achieve the maximum possible separation. The SVM's goal is to create the widest cushion it can between the different classes. This is what makes it so incredibly robust. By making that gap as big as possible, it's much less likely to get confused by new data points that are kind of close to the edge. It's why SVMs are famous for their accuracy. All right, we've gotten pretty good at putting things into boxes and categories. Now, let's switch gears and open up the regression toolkit. This is all about predicting a specific continuous number. We're not asking if something will happen anymore. We're asking how much or how long. But first, we have to clear up a classic point of confusion. You're going to hear the term logistic regression a lot. Now listen closely. Despite having regression in its name, it is actually a classification algorithm. What it does is predict the probability that something belongs to a class, which you then use to make a final yes or no decision. So just remember that little curveball. Its name's a bit misleading. Now, remember our friend the SVM? Well, it has a sibling for regression, and it's called, you guessed it, support vector regression, or SVR. While the SVM wants to find a boundary between two groups, SVR does the opposite. It tries to fit a line where as many data points as possible fall within a certain boundary, or tube. Any of the points inside that tube just get ignored, which makes SVR really good at spotting the main trend without getting distracted by tiny, insignificant noise. And hey, look who's back. The random forest can do regression too. The logic is pretty much the same. You still have hundreds of decision trees, but instead of each one voting for a category, Each tree predicts a specific number. So what's the final prediction? You just take the average of all the numbers predicted by every single tree in that forest. Simple as that. It smooths out any weird errors and gives you a really solid numerical prediction. Okay, so this is all cool stuff in theory, but where does the rubber really meet the road? Let's look at a super high-stakes, real-world example, how these exact same algorithms are being used to predict when a critical piece of machinery is about to break down, literally preventing disasters before they even have a chance to happen. It all starts with what we call a pipeline. First, you have sensors that are constantly collecting raw vibration data from the equipment. Second, you extract key features from that noisy data. Think of it like a doctor looking at symptoms. They're measuring things like the signal's total energy, its RMS, and how peaky it is, which is called kurtosis. Finally, all those features get fed into a machine learning algorithm, which starts learning to connect specific patterns to a future breakdown. In this slide, this is where it all clicks into place. The support vector machine, the SVM, acts as the lead diagnostician. Its job is to classify the exact type of fault. Is it a problem with a bearing's inner race, the outer race? Then you have the support vector regression, the SVR, playing the role of the fortune teller. It predicts the remaining useful life, or RUL. Literally, how many hours does this part have left? And often, the random forest is the hero that helps identify which of all those vibration features are the most important clues in the first place. So after all of that, let's just zoom out for a second and summarize what we've really learned here. It turns out that this huge, complex world of machine learning prediction really just centers on two basic ideas. At the end of the day, it's always one of these two questions. Classification is always asking, which group? Is this thing faulty? Is this email spam? And regression is always asking, what number? How long until this machine fails? What's the temperature going to be? Every single algorithm we looked at is built to answer one of those two fundamental questions. So if you take anything away from this, let it be these three things. First, machine learning prediction isn't some kind of dark magic. It's just either classifying a category or regressing to find a number. Second, even the most complex algorithms can be understood with simple ideas, like a flowchart or a panel of experts. And most importantly, these tools aren't just sitting in a textbook. They are out there right now, working to keep critical systems safe. And that leaves us with one final thought to chew on. From the shows recommended to you on streaming services, to the route your map app suggests, to the way the power grid manages energy, these two types of prediction are everywhere. So the question is, what other invisible predictions are shaping your world right now? Thanks for watching.